This is the video notes for Unit 7, 7.1b activity, More Things Under Construction. We're going to start with the jumpstart. In the jumpstart it says, like a rhombus, an equilateral triangle has congruent sides. Show and describe how you might locate the third vertex point on an equilateral triangle, given that ST is one of the sides of the equilateral triangle. Since ST is one of the sides of the equilateral triangle, we're going to start by building circles that use ST as the radius. So we'll build two of them. Once we've done that, we see at the top here we've got an intersection. This is actually our third point in our equilateral triangle. So I'm going to add some line segments connecting point A to point S and to point T. I know this is an equilateral triangle because we've used the same radius to get to point E as was used to create these two triangles. And I can prove it by labeling. So I'm going to label that. They should all be 3.02, which they are. Okay. Let's go ahead and move on to our launch. In our launch it says, because regular polygons have rotational symmetry, they can be inscribed in a circle. So they can be drawn inside a circle. The circumscribed circle has its center at the center of rotation and passes through all of the vertices of the regular polygon. We will begin by constructing a hexagon by noticing that a hexagon can be decomposed, that means broken up, into 6 congruent equilateral triangles formed by three of its lines of symmetry. So let's go ahead and do that in our next task. We want to break up this hexagon into 6 equilateral triangles and then show where the center of a circle would be that could go around the hexagon and include all of the vertices of the hexagon, and then draw that circle that would circumscribe the hexagon. So first we're just going to add line segments. Lines of symmetry for a hexagon can go from vertex to vertex. They also can go from midpoint to midpoint, but we don't know exactly where the midpoint is, so let's stick with vertices. Now that we have all our 3 lines of symmetry drawn in, we've identified right here our center of rotational symmetry. Once we've done that, we can actually use that point G to draw a circle that circumscribes the pentagon. This is going to help us go backwards and actually create the hexagon. So that's our next task. It says constructing a regular hexagon inscribed in a circle. So rather than starting with the hexagon, we're going to start with the circle and then go backwards. One thing I want you to notice is that the 6 vertices of the regular hexagon, so if we look at these 6 vertices here, so that one, that one, that one, that one, that one, and that one, they lie on the circle in which the hexagon is inscribed. The 6 sides of the hexagon, so that's these red sides right here, so that one like there, those are called chords of the circle. So a chord goes from a point on the circle to another point on the circle. And the question is, how are the lengths of these chords related to the lengths of the radii from the center of the circle? So is there any relationship between the length of the chord and the relationship of the length of the radii? So I have this line highlighted, that's the diameter, but half of that is the radii. So because these are equilateral triangles, I can actually say that the chords are the same length as the radii. And I can say that because they form the sides of the equilateral triangles. Triangles. Okay. Now, based on knowing that the chords are the same length as the radii, can we use that to inscribe a hexagon inside a circle? So starting with the circle and then building the hexagon. So I'm going to say that we can do this, and I'm going to say that we need to probably establish a point on the edge of the circle. So choose a point on the edge of our circle, and then use that point as the center, and use the radius of our original circle as the radius of a new circle. Then use that point as our center, and the center, the radius of the original circle to create a new circle. And I'll show you what this means right now. Okay, so we're going to establish a point somewhere here on the edge. This will be one of the vertices of my hexagon. Now I want all my chords to be the same length as the radii of this original circle. So I'm going to create a circle center at C back to my original middle. And then do you see these intersection points here? Those are where my next vertices of my hexagon are located. So I'm going to say, okay, that's another one vertex on my hexagon. So I'm going to create another circle back to the middle. Here's another vertex of my hexagon back to the middle. Here's another vertex back to the middle. Here's another vertex back to the middle. And I think I've used all of them, and I've located all 6 vertices. I can add one more circle to make it look complete, but at this point I'm just going to add line segments that connect each of my vertices on my circle to one another. And I can hide these outside circles, kind of like my helper circles, to show how I have my finished product. Okay, and that was just by using congruent circles all the way around the edge of the original circle. Now our next task is to modify the work that we just did, but rather than building a hexagon, we're going to construct an equilateral triangle inscribed in the given circle. It's a very similar construction to what we just did, but rather than having all 6 vertices for the hexagon, we only need 3 for the equilateral triangle. So it's a little bit simpler. We're still going to choose a point for our first vertex on the edge. I'll just go over there, and then we start building circles as we go around. Building circles, they're same radius as the original. Okay, now we have them all built, but when we build our equilateral triangle, we're not going to connect all of those vertices on the edge. We're going to create chords or line segments to every other vertice. So we'll go from E to G, and then G to C, and then C back to E. You can see our inscribed equilateral triangle. And I can hide all these helper circles. I don't need to show them if I don't want to. And there we go. Okay. Our next task is to construct a parallel line through a given point. So it is often useful to be able to construct a parallel line to a given point through a given point. For example, suppose we want to construct a line parallel to AB. So here's the image right there. We want it to be parallel to AB, but through the point C. Since we have observed that parallel lines have the same slope, the line through point C will be the parallel to AB only if the angle formed by the line and BC is congruent. So we want to mimic this same angle here. So I think that this is all about adding circles, but not necessarily circles with the same radius. Add circles. And copy them to different centers. But they are not congruent circles. I'll show you what I mean. So we want to mimic this angle, right? So the first circle I'm going to draw is from B to A. Now, that establishes the distance from that I want to go from C to my final point, somewhere out here, right? Somewhere out here is my final point over here somewhere. Okay, so if I want to mimic this like this, I probably need to copy this circle over to center at C, right? Because I'm trying to mimic that angle right there. So my fourth point will be somewhere on this little circle. Okay, now that I've established kind of the angle, I need to figure out how far away my last point is right here from A. So now I need to like mimic this right here. So I'm going to draw another circle. This one will be bigger. And that will be copied. So I'll do center at B over to C, and I'll copy that over to over here to center at A to help me pinpoint this location right here, right there. Okay. So then I can add a point here, and I've created, well, I also need to add a line segment. I've created a line that is parallel to AB, but goes through a different point, goes through point C. Now this skill right here will actually be really useful to build a parallelogram, because this is almost a parallelogram right here. In order to finish the parallelogram, we would just connect A to D, and then it would be done. Okay, so this is a good skill to have to draw parallel lines for the construction of a parallelogram. Okay. To finish up, we've got a few takeaways. So what can we do to construct geometric figures? So I just want you to list maybe 2 or 3 things. These are the ones that were helpful to me. It was really helpful, so I'm going to say my first one is to use congruent circles, but just change the center of the circle. So that was really helpful. Okay, what was another one that was helpful? Maybe think of my constructions as also transformations. Like, I don't know if you noticed on the parallel line that we just did, I was sketching in what I want it to look like, and kind of almost doing a translation of the original line AB to its new location. So I could use rigid transformations to help me visualize it. I could also sketch what I want it to look like. So that will be my third one. Make a sketch of what I want it to look like. So that was pretty helpful. Okay. One other thing that I thought of, so I thought of a fourth one, it's really helpful to know the properties of the shapes. So in Unit 6, we learned all about rectangles, squares, parallelograms, and rhombus. And so it's really good really, really helpful here to remember the properties of those shapes. Remember the properties of the shapes. And we already covered that from Unit 6. So that was really helpful. Okay. I hope that this video is helpful to you in completing the 7.1b activity, and I wish you best of luck on your practice. Thank you.